day or two.
Well,
Well, I heard Friday was way worse than Saturday in terms of
Yeah, it was way better
sound
on
quality.
Saturday, but like, because Friday was like one of the first times we were using the actual like sound system, and so it was Sean, like our sound guy, who was trying to like figure out how to like blend and mediate certain vocals and instruments, and so it's like he was just having a hard time with it.
well, then you have to balance it in two places, right? It's not just balancing it within the room, but it's balancing it within the room and then on the computer on the street. Yeah, so I'm sure it's an absolute nightmare.
Oh yeah.
Anyway, so let's keep going here. We were in 9.7 last week Thursday, and I introduced what's known as a galvanic cell. A galvanic cell is a battery. All right. There's multiple names for this, and I did point these out last week. Sometimes they use the word galvanic, sometimes they use the word electrochemical, and sometimes they use the word voltaic. They all mean the exact same thing, and it's basically describing a redox reaction where we've separated the two halves in order to direct the electrons transferred through a wire. Okay? The idea here is if we can separate our two halves of the redox reaction, we can allow the electron transfer to occur, and we can control where the electrons go. And as a result, we're generating electricity. And we can use that to do work, power devices, all sorts of things. Okay? So we drew this diagram, and a couple big takeaways that I wanted to give you. The anode is one of the names of the electrode. The cathode is the name of the other. The anode is where oxidation occurs. All right? Vowel. Okay, or red cat, people were using as well. I don't care. All right? But oxidation, which is half of our redox process, occurs at the anode. Reduction, the other half, occurs at the cathode. Oxidation is what? What occurs in oxidation? More specific? Leaving, yes. Electrons are lost. In reduction, electrons are gained. Oil rig, right? That's the old mnemonic from last year. Still true, still applies. And with a galvanic cell, we're basically just needing to identify where each half is occurring, understanding that if oxidation is happening over here, the electrons are leaving. Okay, come on. Quit fighting me. And then going through our wire, and then being gained on the side of the cathode, where reduction is happening. Okay. Any questions from last week Thursday at all? We'll certainly do a little bit more here in the near future. Some of this is reviewed today. A decent little chunk of this is reviewed today from last year. Because you guys did do voltages last year, did you not? Like half reactions where you just have two halves and you add up the voltages to get the.
No.
No, come on.
No, we just did reduction. Yeah, like they slowed way down. Like we stopped kind of at redox stuff.
Gotcha.
Oxidation and reduction. So I'm guessing this is something we would have learned at the end of the year.
Yeah, not this complicated, but yeah. Don't worry, it's not too bad, I guess. You didn't learn it. Maybe you'll remember it. Let's see. So a couple things about batteries, a couple things about voltage, and a little side context, I guess, just in general. So a capital V represents the unit of volts. Can't go wrong with purple. Okay? It is a unit of electrical potential and defined as 1 joule per coulomb. Now, coulomb is the unit of charge. We'll talk about coulombs in just a little bit. We'll get to that tomorrow and the day after. But a volt is a joule per coulomb. Coulomb, or capital C is for coulomb. Charge of an electron is 1.602 times 10 to the negative 19 coulombs. So the polar driving force on electrons in a galvanic cell is called the cell potential, or electromotive force, and has units of volts. What is the voltage of various batteries pictured below, the left in your page? So the batteries you're familiar with most often in your life are AA's, AAA's, C's, and D's. But even C's and D's you hardly ever see, right? AA's, AAA's are really what you're familiar with. Does anyone know the voltage of those batteries? Double A's are 1.5 volts.
Why are they called double A's?
Yeah, what are the letters?
Size. The letters are referencing size.
What size? Like,
I don't know. It's kind of an arbitrary.
yeah, no, I don't really get the whole letter
Single A
sizing
battery?
thing.
I don't think so. If there is, it's not made anymore.
Because they're double.
Maybe. I don't know.
If it's for size, it's double A.
Yep. Double A is bigger. C is bigger. D is the biggest. For all of our battery sizes. So yes, double A is bigger than triple A. This is 1.5 volts. This is 1.5 volts. This is 1.5 volts. Oops. Great question.
The battery life.
Bigger equals more stuff. More stuff means it's going to last longer. So they all actually are the exact same chemical reaction occurring. Okay, all of the standard batteries that we use in our lives, again, mainly double A's and triple A's, okay, they're both those batteries are undergoing the exact same redox process, and their potential is 1.5 volts. Okay, so again, why are there different sizes if they're all going to provide the exact same amount of voltage? Well, bigger battery, more chemicals on the inside, it'll last longer. So you can totally rig up your TV remote with a D battery. Have you seen D batteries before? Big beefy ones. Yeah. The only thing I remember using D batteries for in my life was my kids' baby swing when they were little. That sucker took 4 D batteries. Well, not. I mean, it was all right, you know.
Why would we use a new battery for everything?
Well, generally, when you need that much, like if you need something that requires that large of a battery, you generally just end up getting like an AC adapter, right? A lot of like things that require a prolonged source of energy are going to usually have like a plug. Because that's just way the heck easier than trying to finagle with. Yeah, so I don't know why our baby swing use batteries as opposed to just having like an AC adapter. That would have been more appropriate probably for the end game of that, but whatever.
So then why do some things require two double A?
It's just quantity. I mean, no, you could
Is that length as well?
Yeah.
So then why would we?
Is it just for the money, do you think?
I don't
Is it
think
for
so.
like?
I mean,
engineering?
okay,
Why
so-
not just one uniform size?
Yeah.
there kind of could be. I mean, the reason why you use AAA for certain things, right, is like profile. Again, your TV remote's kind of thin and skinny usually, so it's nice to have batteries that obviously fit well within that size, and it's not, you know, big and bulky and ugly. So really, like the size of the batteries is twofold, I suppose. It's a combination of whatever size end product you're trying to produce, but also how long it needs to last. So here's where I was going with this. You can totally take your TV remote and rig it up and hook it up to a D battery. It would work, same voltage. So there'd be no like issue in terms of like the electricity that's being provided for your remote, and you'd never have to change the batteries on your remote for like, I don't know, good 4 or 5 years. But then you'd have like this giant D battery, you know, hanging off your remote.
Then why would you have the difference between the triple A and the double A if there's such a small
Yeah.
money at that point?
I think it's size. I think I think of children's toys. That's where a lot of the batteries in my household go towards, right? Is my kids' toys.
Yeah.
There are tiny little toys that like AA batteries would just increase the profile size or the size of it. So I don't know. Maybe there's, I don't know. Maybe it's a little bit overkill to have more sizes, but
Is there a B battery?
no, there's a.
Why'd they just skip B?
You know,
Why make
I have no
double A, triple A, and not just A, B, C, D?
Great question. Jaeger, I don't know. Great question.
Shouldn't the double A just be A?
That's what
Another
I'm
great
saying.
question.
If you just use B, there would be the double, triple A thing.
All right.
A, B, C, D.
All battery naming obscurity questions aside,
So,
let's keep going. Okay, that's good. So the zinc oxidation half reaction has a potential of positive 0.76 volts. Do you have last year's periodic table?
Probably not.
Well,
yeah,
I think someone stole it.
I have a periodic table.
If you go to last year's periodic table and you flip it to the backside, Top center on the back side.
We did this.
You did this. Excellent. Okay, I thought you might have. On the back side of last year's periodic table, on the top middle, there's a chart, and the title of the chart is called Standard Reduction Potential. What this is the voltage provided, or the potential provided, for each of these half reactions in the reduction direction. Have a great day. If I don't want reduction, but I want oxidation, what do? Flip it. And if I flip it, what do I do to the sign of my voltage? Flip it. Yeah, it's that easy.
Oh, wait, did we do this?
Yeah, you probably did. Okay, so if you find the zinc one, okay, and I look up zinc, zinc is number 12 on the list. And the way it's written right now is it's written as reduction, because all of these are reduction, okay? But the way I'm using it here on my slide, I have it written as oxidation. So on the chart, it says negative 0.76, but for me, I've flipped it, and it's a positive 0.76. Okay? Very, very simple thing to use and read and figure out. So to balance this with the reduction of aluminum, you would need to multiply the oxidation half reaction by 3 and the reduction half reaction by 2, right? If we were balancing it the old-fashioned way like we used to, where we do the oxidation numbers, we figure out what's oxidized, what's reduced, we take down one half, we take down the other half, we balance each half independently, then we combine the halves, remember that? And then the thing with the electrons is however many electrons I lose needs to match however many electrons I gain. I cannot gain or lose more electrons than the other half reaction allows. So long story short, in this instance, I'm losing 2 electrons from the zinc. I'm gaining 3 electrons in the aluminum ions. Those don't match. So what would I have to do to balance this? Well, I'd have to multiply my top oxidation half reaction by 3. I'd have to multiply my bottom reduction half reaction by 2, so that I'm gaining and losing the exact same quantity of electrons. Sound familiar? Cool. When you triple the oxidation half reaction, the electrical potential does not change.
So, like,
It is important.
the voltage doesn't change.
Correct.
I guess that makes sense.
The potential is an inherent property of the chemical substance. In other words, it does not matter how many times this half reaction occurs. It just matters what it is. It's zinc being oxidized to zinc 2+. That process has a potential of 0.76 volts. If it occurs one time, excellent, 0.76 volts. If it occurs 6 times, excellent, 0.76 volts. Moral of the story is this: when it comes to potential, aka voltages of half reactions and redox, however many times the process occurs is irrelevant. The voltage is based off of the chemical substance, not the quantity or the number of times it happens.
So this is like potential. Is there like something that's real that's like different?
So voltage is called potential because until you make it do something, it's like it has the potential to do, the ability to do work in the future if you apply it to the system. It's weird. We're approaching physicsy stuff, and man,
Okay, so
I'm not interested in that.
the difference between like voltage and amps is like voltage the speed at which electricity is moving, and what is it?
I don't want to talk about. I don't want to go there yet.
Not yet.
Not yet.
Is that gonna be relevant, or is that a bad?
We'll talk about current
Okay.
on Thursday. So yes, we will discuss the difference between potential, current, and a few of these things later. But I don't want to put the cart in front of the horse.
I can't help but notice, but there isn't a review in the package.
Oh yeah,
That was, yeah.
So,
No test.
for Unit 9, we're gonna ignore a summative. Now,
So let's not tell Luca and Logan and just like make them like
Why would I choose to do that with 2 weeks prior to the AP test?
Because you shouldn't be worrying about
One or the other.
Because there's 2 weeks prior to the AP test. Yeah, I mean, I want your focus not on your grade in my class right now. I want your focus on the AP test. So yes, we will finish the content, make sure you know what you need to know. But in reality, this is the most recent one. So I like your chances of this content being pretty solid on the AP test. So the test in this class, whatever. I don't want to waste a day. I don't want to waste your brain power. I don't want to waste your focus. I'd rather have you focused on getting ready for May 7th.
But I definitely freed up a lot of stress.
Good.
Yeah,
You like I can
really
sleep
thank you.
easier now.
Good. All right, so meaning,
Sleep at
so the electrical potential does not change regardless of how many times it occurs, meaning that regardless of the number of times that a half reaction occurs, the oxidation or reduction potential of that process is always the same value. A large D battery is made from the same materials and has the same chemical potential as a AAA battery. However, the D battery will last longer. Standard oxidation or reduction potential is an intensive property, which means it does not depend upon how many times the reaction occurs. When we use the word standard, same meaning as before, okay, we're implying that we have 1 molar solutions, 1 atmospheric pressure, and 25 degrees Celsius. There's a table of standard reduction potentials on your periodic table. We already kind of looked at that. The word standard here and the degree symbol that shows up is the exact same meaning as it was previously with the thermodynamic stuff in 9.1, 9.2, 9.3. Okay? Anything with that little degree symbol is implying standard conditions. Where? There we go. If I write the zinc half reaction backwards, what happens to the potential of the half reaction? Here's the oxidation half. Here's the reduction half. What happens? You just flip the sign. I flipped the reaction. I flipped the potential. Pretty easy peasy. You'll need to do it quite a bit. The reason why you're going to need to do it quite a bit is because these are all reduction. If I want to have a chemical reaction occur, I need an oxidation, right? If I'm going to have redox reactions happen, I need half to be reduction, half to be oxidation. I need both processes in order for something to happen.
It'd be
Like zinc metal turned into zinc ions and zinc ions turned into zinc metal.
yeah.
That would be at equilibrium, so literally nothing would occur. Now,
Yeah, because you don't want.
yeah, equilibrium is a dead battery. When equilibrium is reached in a redox process, your battery is dead and no longer providing any usefulness. However, you can set it up in a way where you have both the same oxidation and reduction, but you need to mess with conditions in order to make it do something for you. We'll talk about that on tomorrow or Wednesday.
Okay.
So that does come up. Good question. Getting back to the first example, so the beaker, the 2 beaker system, the galvanic cell that we drew at the top of this sheet, I was using magnesium and copper. Okay, let's find these on here and give the overall process. The magnesium is going to get oxidized in that galvanic cell. The copper ions are going to get reduced. Let's find those on here just for the sake of argument. By the way, do you see this little chart? In that textbook, which I don't have up here because I don't have my cart, but in the textbook, it's got like 4 times as many of these. Yeah, there's a lot. And they get way more complicated than like single metal ion. You turn it into single metal substance. There's all sorts of weird half reactions in a normal reduction potential chart. And there's way more than just this little list that we gave you in regular chem. But anyway, let's find the magnesium one. What would be the oxidation potential of magnesium based off of this? Positive, 2.37. When you look it up, again, they're all written as reduction, so it's negative right now, but we're not using it as reduction, we're using it as oxidation. We flip the sign. The next one, copper being reduced. What's the reduction potential of copper? Now, when I write this with voltages, I generally do use positive signs. Okay, that's kind of normally it's very much implied, but with voltages, I don't know. I like it. You can not write the positive sign if you don't want to. What I'll tell you is that generally speaking, if you see a redox galvanic cell question on the AP test, they will write positive signs as well. Okay, so they're pretty explicit about positive, negative when it comes to galvanic cells and redox. Anyway, so here's the overall process. Here's the oxidation potential. Here's the reduction potential. What's the overall potential? You just had them. How exciting. And that's it. Okay. Now, what's also really important is that the direction of the redox reaction that gives you a positive cell potential. By the way, this right here is known as cell potential. The symbol of this is capital E. It's usually like a funky stylized E, but AP's gotten rid of the funky stylizing of it. So they just use capital E. And then subscript cell, like this. But that's, whenever you see this symbol, that is implying what's the voltage of your battery, what's the voltage of your galvanic cell, okay? Galvanic, electrochemical, voltaic cell, either of those terms, any of those terms.
So that's for positive or negative voltage?
Correct. Okay. This is simply saying what is the voltage of your redox process. In this instance, it's positive. When you have a positive cell potential, it is thermodynamically favorable. Okay. We've already come across a couple other instances comparing chemical reactions to thermodynamic favorability, right? Delta G, that is Gibbs free energy. When delta G is negative, you have a thermodynamically favorable process. When delta G is positive, you have a thermodynamically unfavorable process, meaning it's not going to happen. When it comes to potential and galvanic cells, we are looking for a positive cell potential. A positive quantity of volts implies that you do have a thermodynamically favorable process. This is a working battery. It's going to do something for us. It's going to react. It's going to go in this direction. Okay? So will the reverse reaction be thermodynamically favorable? If I flip this thing, okay, the whole process, right? If I flip it, my battery's still going to do something?
Yes. Well, someone has to say.
I appreciate it. No. What happens if I flip this whole process? What do I get? I get negative 2.71. Yeah, literally, it wouldn't do a darn thing.
Oh, yeah,
Wait,
it's
what?
not thermodynamically favorable.
They were thermodynamically unfavorable, yes. Or not thermodynamically favorable, however you would like to say it. Yeah. So if it's negative, it's not going to do anything. Because that's not the direction of spontaneity. That's not the direction that it's going to spontaneously proceed. If it's positive, that is the direction it's going to go, right? It'll naturally, inherently proceed in that direction. The explanation here, the cell potential, standard cell potential, would be negative. Okay, if I flip the whole thing, my cell potential is now negative. And that means that my battery's not going to work. Fill the table to see if nickel ions will oxidize tin metal. What we're looking for here is to have a reaction occur with nickel ions and tin metal. That's a good question. What I have provided for you are the reactants. This is a reactant. That is a reactant. In other words, I'm forcing you to pick the appropriate direction in both of your half reactions. You don't have the option of like flipping one or sorry, you don't have the option of like deciding which way they both go. I'm telling you, you've got nickel ions. The only possible direction you go is to turn into nickel metal. I'm telling you, you've got tin metal. The only possible direction it can go is to turn it to tin ions. Does that make sense?
So yeah, and you say oxidize. So oxidize.
Yeah. Yeah, which means that we need to flip it, right? Because this is reduction. Okay, so let's find oxidation. Tin, what's the chemical symbol for tin? SN. Makes sense. Okay, so I find tin. It looks like it's equation number 7 on your old periodic table. And the reduction potential of tin is negative 1.14. The oxidation potential of tin is positive 0.14. I find the reduction potential of nickel. There it is. Nickel 2 plus turning into nickel metal. Sorry. Break goes on the appropriate side, my bad. The reduction potential of nickel is negative 0.25 volts. The overall process, I'm gaining 2 electrons, I'm losing 2 electrons, so the balancing would be ridiculously easy if we did the whole thing, right? Again, the whole end goal of this process is to make sure that we lose and gain the exact same quantity of electrons. But we're good. I'm just going to have tin plus nickel 2 plus yielding nickel metal and tin 2 plus. What's the potential of this redox reaction? What's the potential of this redox reaction? .11?
Yeah.
So, is this going to be a good battery? No, it's not going to do a darn thing. Okay, this is not going to be useful. It's not going to work. How could I make this a working battery? Go the other way. Now, it would only be providing me 0.11 volts of potential, but that's at least positive. If it's negative, I can't do a darn thing. So if I flip this whole process, and instead of having tin metal and nickel ions, if I instead had nickel metal and tin ions, the reaction actually would happen, because that is the direction that it is thermodynamically favorable. Positive cell potential equals thermodynamically favorable. Negative cell potential equals thermodynamically unfavorable, or not thermodynamically favorable, however you'd like to say that. Okay, so let's take that and let's make it actually work. Let's pick the direction that makes a working galvanic cell, voltaic cell, electrochemical cell. And I would like to draw this diagram out one more time, but this time we're going to use tin and nickel instead. Okay. I do want the electrons going from my left chamber into my right chamber, like we did on the very first example. But please, if you could, use the first page of this to help you out with this. Label my diagram. Label your diagram. Put all of these pieces in there. I'll give you a couple minutes, and then I'll jump in and finalize this and figure it out. Electrons are being lost on the left-hand side, transferring through my wire, and being gained on the right-hand side. What process is occurring in the left-hand beaker? Oxidation. Okay. That's just identifying what's happening, right? Again, how is this different than normal redox? Normal redox just occurs, like in one location, right? We mix everything together and it just happens in a beaker, in a reaction chamber, whatever it might be. But the reason why this is unique, the reason why this is different, and why it's important is because we are taking our two halves, separating them. And when we do that, we are directing the flow of electrons. When electrons are flowing through a wire, that is electricity. It can do work. Right? That is the whole point of this. That's the reason why this is a big deal. And again, in modern day society, the usage of batteries, understanding how batteries work, developing better batteries that last longer, are rechargeable. Okay? It's all very relevant stuff. But anyway, okay, so oxidation is occurring over here. What do we say? Let's go back to our previous slide. We had set it up this way originally, but it wasn't going to work, right? So I don't want this. I want the opposite of this. So what's going to be my oxidation? The nickel. Yeah. I tried to set it up this way, but it wasn't going to do a darn thing. We want the positive cell potential direction. We want the direction of a positive voltage. So I'm going to need the nickel over here. I've got nickel, and I've got nickel 2+. How do I label that? Well, where?
Just throw it in like the left beaker.
So the nickel 2+ is aqueous, meaning it's like in solution. It's the liquid inside the beaker. The other nickel, which is nickel solid, is my electrode. This piece of metal right here would be nickel metal, or would be nickel, yeah, sorry. Okay. So the electrode itself would be made out of nickel. And in the beaker, I would have nickel ions. And what happens is when these two things are in contact with one another, and we complete our circuit and we do the whole rest of this stuff, right? This is being oxidized. The nickel metal is being oxidized into nickel ions. And as that process occurs, it loses electrons. Those electrons are directed through the wire to enter the other side, where our reduction is happening. On the other side, we are reducing tin. Again, the ions, which again, ions don't exist by themselves, right? I talked about this too when we were talking about buffers. If I want to make a buffer, I need weak acid and its conjugate base. Well, how do I get the conjugate base in my solution? Well, I need a salt, right? I need something that can counterbalance that charge. And charges aren't going to be stable, or charged particles or ions aren't stable unless there's something else there. If I mix it in water and it's aqueous, then I can stabilize. So my tin ions are in solution over here, and my electrode is going to be tin solid, tin metal. Okay. So this is oxidation. What are we going to call this electrode? It's nickel. That's the material it's made out of. But what are we going to call that electrode in terms of my? That's the anode. How do I know to call that the anode? Oxidation occurs at the anode. This is the cathode. Reduction occurs at the cathode. Okay. What am I missing here? Wire. Okay, lost the wire. That's salt. The salt. This is my voltmeter. The voltmeter, all that is measuring my potential, right? So in other words, this is what's telling me that it equals 0.11 volts. The device that can tell you the voltage of your system. Is that it? Salt bridge. I'm sorry. Salt bridge. Now, what's the purpose of the salt bridge? It is full of salt, a solution of salt, aqueous salt. Yeah, I need to complete my circuit. Now, here's the issue. Without the salt bridge, I would have oxidation and I would have reduction, and they would start, but it would stop almost like instantly. I would reach equilibrium extremely fast. Because the instant that I'm starting to lose electrons from this side and gain electrons on this side, I would get a very positively charged solution over here, an excess of positive charge, and I would get an excess of negative charge. And then I'm going to reach equilibrium and nothing happens, and I got a dead battery. What the salt bridge does is it completes the circuit and provides spectator ions to either side. When the electrons are leaving my oxidation half of the cell, the salt bridge provides negatively charged ions to counterbalance that and keep it neutral. When the electrons are entering my reduction half of the cell, the salt bridge is providing positive ions to keep that side neutral. I need to complete the circuit. I need random spectator ions to keep the charges neutral. If both sides of my cell can remain neutral in charge, this process can continually occur and keep going and keep happening until I run out of like a reactant, right, or a raw material. But without the salt bridge, I don't have a complete circuit. I get an instant buildup of charge and it just stops working.
What salt would you want?
Something that doesn't mess with my reaction, right? Now, this is a little different than acid base. In acid base, it was always like, oh, we want neutral ions, right? It was always like, oh, let's pick sodium. Sodium is great and it's neutral and it's not going to mess with anything with our acid-base chemistry. The hard part with redox is different ions have different reduction or oxidation potentials. You would want to pick an ion that has a hard time getting oxidized to enter over here, right? And you want to pick an ion that has a hard time getting reduced over here. In other words, I don't want my ions messing up what I'm trying to accomplish. So it really depends upon what the other stuff is. But yeah, you'd want to pick a salt in your salt bridge that effectively doesn't have any influence on the battery except for providing positively or negatively charged ions to keep things smooth.
Would that ever be like a
No, no. No, they would not have you select a salt for your salt bridge. Yes.
Okay, so the electrons moving through the voltmeter and the wire, that's what's generating electricity we use, right?
Correct.
So how do you know when you run out of raw material?
So yeah, so here's the deal, right? On this side, I'm oxidizing the nickel.
Yeah.
If my electrode's literally like going away, the metal of this material is literally losing mass.
Okay, so it's deteriorating.
Yeah. If I run out of nickel, well then my battery's dead. Over here, it's the same thing in solution. I'm reducing the tin ions into tin metal. If my molarity here is like 1 molar, but I run out, my battery's dead as well. So yeah, in an ideal world, we set up a battery to die or to stop working when we run out of reactant, right? The reactants in this cell are the nickel metal and the tin ions, because I'm oxidizing the nickel metal and I'm reducing the tin ions. If I run out of either, my battery's done. But again, the salt bridge is important because then that doesn't, it lets the battery go as long as it can until one of our reactants runs out, until we have a limiting reactant question or problem. Cool? Yeah?
If we had a lab, like if we were doing
Yeah, so what I have for redox labs is we do the electrolysis of water normally in this class, which is like forcing the galvanic cell to run backwards. So we would do the electrolysis of water. And I also had a lab where we make batteries out of fruit.
The lemons work really good.
Lemons work really, really well, yes. Okay. So yeah, we did the cell potential of various electrodes in fruit as well.
Have you ever tried something like a watermelon?
I have not. Sure, it would work well. I mean, it's a high water content. Again, the juicier the fruit, the more you can kind of.
So when you get like when you touch a piece of metal and you get yourself shocked, that's like static electricity. Like
Uh-huh.
It's just the transfer of electrons. It only have it for an instant because then it's.
Well, you get shocked once, right? If you try to
Yeah.
touch it again, your buildup of charge is dissipated at that point
Yeah,
until you do this.
right.
Yeah, and then you build it up again and charge it. I've got 10 minutes.
Let's not start that.
Yeah, it's Monday. I don't want to.
Oh,
I mean, this completely different.
It's not completely different. So
I see Faraday constant, that looks familiar.
it's in your formula packet. Your homework topic 1 is due tomorrow. I think it was super easy. You might or may not like even need to do anything on it still. But homework topic 1 is due tomorrow. If you have any AP questions over the last 10 minutes, that would be cool. I can totally help you there and answer those if you're deep in the middle of the test. Does anyone need the 2017 multiple choice test? I think I had fewer people take it, which either A means that the third one, yeah. Okay. Free response stuff, anyone? I did, but I want to make sure you're looking at them and
There's so
doing
much
them.
stuff online for free response. There's a lot more free response stuff online than
Yes.
there is.
100%.
Like I tried to just search up like a multiple choice section and
Yeah.
I couldn't find it.
Nope, good. You're not really supposed to be able to find any of those.
So what starts this reaction? Like once you close the circuit, it will start immediately?
Mhm.
So even like a AA battery, you have this system, right?
Mhm.
So if it's just sitting idle,